Hello, today we're going to be talking about parameterizing curves. And this is a pretty important topic in vector calculus because, in the past we've dealt with lines in two dimensions using equations like y equals mx plus b, and other types of equations too, like for example, any equation where x is the independent variable and y is the dependent variable. What that means is that with these equations, you pick an x, so I want to know what happens at x2. And then depending on what you pick for x, you will get a value y. And so because we have our axes orientated that way, we call x the independent variable because nothing that y can do will affect x, whereas x, wherever you choose x to be, will give you a y value. So in terms of nomenclature, we call that the independent, so in other words, it depends on nothing, and the dependent variable. So we found ways to write equations, and we may have even parameterized things in two dimensions, like probably at the end of Calc 2 you did some finding the areas of parametric shapes. But now in Calc 3 we've moved into the third dimension, and that can be kind of tricky because you'll notice this equation y equals mx plus b that I have plotted up here. I've now flipped the axes, no, not flipped them, I've rotated it and placed the x and the y there, and here's our line y equals mx plus b. Well, you'll notice here that this equation only has to do with y and x. But now, because it's in 3 space, it is now a function of x, y, and z. So, because it's a function of x, y, and z, that does not matter what z you pick. In other words, we could add in here, we could say plus 0z, because no z that you can pick will change where this line is. What that means is that there are infinitely many lines of this orientation that will move up the z-axis, because it doesn't matter. It doesn't matter what z you're at as long as you have the right x's and y's that match mx plus b here. So in other words, we could keep drawing these lines, infinitely many of them, and what that ends up forming is a plane. And so our problem in 3 dimensions is that without parametric equations, we end up with planes if we try to use y equals mx plus b. And so because of this, we need to introduce a third variable that's not x, y, or z. It's actually going to be t. And what's so cool about that is, to build a line in 3 dimensions, you actually need time, which really, I think, reflects philosophically a little bit as to why we have time in 3 dimensions. It's because we need it to have a path that isn't spread out everywhere like a plane. And so let's start with parameterization and parameterizing something that we're familiar with in 2 dimensions. So if that's our x-axis and our y-axis, let's use the famous parabola y equals x squared. So in this case, x is our dependent variable, x is our independent variable, y is our dependent variable. But what if I wanted to, let's see here, what if I wanted to replace, let's say I wanted to replace x with a function of t and y with a function of t. Well, I could go ahead and start a substitution and say let x equal t, right? So now x equals t. Well, what does y equal? Well, if I plug in t for x, y equals t squared. So now y equals t squared. So now x as a function of t is just t. Y as a function of t is t squared. So let's go ahead and pick some times. Let's pick when t is 1. Well, when t is 1, x of t is 1, because we're plugging in t there. And when t is 1, t squared, 1 squared is just 1. So y of t is also 1. So at time 1, you could almost draw a vector with the x component in terms of t and the y component in terms of t. And this vector is going to point to time 1. So there's time equals 1. That's when y equals 1 and x equals 1. But what we really want to imagine when we're talking about a vector parametric equation is we're thinking about there is a line from the origin of our Cartesian coordinates that is pointing towards where we're at now. Now at time 2, when t equals 2, what we end up with is x of 2 is 2, and y of 2 is 4, because 2 squared is 4. And so now what we're looking at is we're looking at a vector that's pointing to t equals 2, the point t equals 2, which happens to have coordinates 2 in the x, 4 in the y. And we will typically write this equation as r with a vector sign over it of t. So it's where you're at. R is commonly used to denote position. So where you're at in terms of a vector, so this vector is going to point to where you're at. And to write that in a different form, we could say it's equal to the vector of x as a function of t in the I hat direction times y as a function of t in the j hat direction. This also extends to the z direction as well, or the k hat direction. So now that we've seen that in 2 dimensions, let's go ahead and throw it into 3 dimensions, and we'll save the cool shape, the parabola shape, but we'll put it in 3 dimensions. So let's say that we have, let's draw it this way. So here's our z direction, our x, and our positive y direction. So what if we wanted a parabolic trajectory in 3 dimensions, but we didn't just want it to be on the x-plane or on the y-plane? Let's split the difference. Well, we remember that for a parabola, we ended up doing t and t squared. Let's go ahead and try. For x, we'll say it's t, for y, it's t, and for z, it's t squared. And so this is another way of writing x is a function of t, y is a function of t, and z is a function of t. And so this is going to be our position vector as a function of time. And so you'll notice here that at time equals 1, if t equals 1, that our position vector r of 1 is going to equal 1, 1, 1. So we can go ahead and find that. That's 1, that's 1, that's 1. So we're roughly looking at something like that. Here's t equals 1. And then when t equals 2, we end up with 2, 2, 4, which ends up kind of being above where I'm supposed to be at, but we'll just draw it here. T equals 2. And what we end up with is we end up with a line that traces out this curve. However, I want you to imagine that for every point on the curve, there is a vector arrow starting from the origin pointing to where it's at. And that is our r vector at any given point in time. All right, so that just about covers it for parameterization. Yeah, it is interesting because it does trace out a line, but the truth is that the equations themselves for r of t is going to be a vector starting from the origin. So when you think of r, for example, if I drew this line, and let's say that I have my x and y axes here. If I draw this parameterized curve, you don't think about the r vector as like, don't think about the r vector as pointing in the direction that the line is going. That's not what the r vector is. We'll talk about what that vector is. That's a different vector. It's called the unit